Okay, so at this point we're going to go into the water balance calculator. So here the screen that you see right now is what you get when you log into Smarts, and basically under the construction permit. This is all under the notice of intent interactive screen in the first menu. So what I've done here is pulled up the tabs that apply to construction permits. And so we have a fictitious project. It's down in Beaumont, down in Southern California, in Region 8 in our water board. And so there's a post-construction tab, so that's basically what we're going to be dealing with. There's other tabs here as well, and so Patrick Otsuji and others do some really good Smarts training for the water board. We're just going to deal with this particular tab here, the post-construction tab. So we're just going to walk through each of the questions that it asks. It's pretty interactive. It's asking you questions, and then there's just a series of sort of pull-down yes/no answers. And you sort of work through. It's very sort of linear, so you just work through and answer all the questions, and the appropriate follow-up questions or pop-up menus will come up depending on your response. So what it's first going to ask you is whether your project, your construction project, is within a permitted Phase 1 or Phase 2 municipal separate storm sewer system area, or MS4. So stormwater is a very acronym heavy business, so there's a lot of acronyms in here. What I'll do is I'll explain. I think this Smarts program does a pretty good job of laying out what each of these acronyms mean. But the first one is MS4, and so these are municipal permits that the Phase 1 MS4 permits are written by the individual regional boards, and the Phase 2 general permit is basically a statewide general permit that the smaller municipalities apply for coverage under. So the first question is basically asking you, does your project lie within a permitted Phase 1 or Phase 2 area? And so that's relevant, because if it does, then the project is held to the standard that's in that Phase 1 or Phase 2 permit. So it's kind of a sort of a cookie cutter binary approach. You're either in or you're out. So what I'm going to do here is select, because we basically want to work through the calculator. If we select yes, it's going to give you basically that this calculator doesn't apply. But let's put no, and then the next question it's going to ask you is, will the project use an alternative method to calculate runoff volume? So we'll go. I'll explain what sort of the background is and the calculations and the runoff prediction methodology that's used in the calculator in the next few slides. But suffice to say, you can use a different method to demonstrate compliance with this water balance standard if you want to. And so it's asking a question relative to that. And it's also asking if you're going to use different design measures than the 9 that I mentioned on that list before. So in this case, just for example, we're going to say no, because we actually want to work through the calculator and show you what the different credits are and how they work. And then it asks you, will a project be subdivided into smaller sub-areas or drainage management areas? And so one of the things the water board wanted to do was allow people the ability to sort of mimic the drainage layout that is done in a drainage plan or a flood control plan, not depart radically from the delineation that's already been done to quantify hydrology on the site. So in this case, I'm going to put no, because we'll have kind of a simple, straightforward project to illustrate how the calculator works. But you do have the option. In fact, it's probably suggested that you just mimic the drainage management areas that you've delineated for flood control. Like a 10-acre project, you generally don't want to channel everything to sort of the corner of the project. I mean, it's going to be much easier to manage runoff on a sort of a distributed basis and smaller runoff drainage management area basis. So I'll select no for that. And so this message pops up from the web page basically saying, okay, are you sure? You've chosen no. And what this does is it's just going to give you one screen that you have to fill out for the entire project. So we're basically considering the one project as one big drainage area. So I'll select OK for that. Okay, so then we have a whole series of inputs for watershed and project information. So for 1A here, I'm basically going to call it proposed elementary school. So we've got proposed elementary school, and we're going to put, let's put Riverside County. So kind of like Russell too that we talked about in the previous section, it's doing some real-time updates in the calculator. So Riverside was selected here, and so what that's doing is that's pulling up all the relevant rain gauges that are in Riverside County. So it's a matter of knowing how close your project is to the rain gauge. So this happens to be a project that has a rain gauge nearby. So just a little bit of word about rainfall information. I mean, that's highly sensitive to elevation, and that's something that you definitely need some good professional judgment on. I mean, in California, you really have extremely variable rainfall depths depending on mountain range influences, sort of, we call it orographic effects. I mean, so it's incredibly sensitive to a lot of topographic features. So you might have to do a little bit of homework. The calculator doesn't really have much guidance on which gauge to select. So I would suggest going to your local, flood control agency, or the water worker can provide technical assistance on which rain gauge to select. But this happens to be the Beaumont gauge, so we'll select that. And that's relevant because that's going to pull in the 85th percentile storm event. So that's very much location specific. So in this case, we're going to pull that data from the Beaumont gauge, and that'll show up later on in the calculator, and I'll show you that. So let's say, nice round number, let's say it's a 10-acre project. And then it's going to ask you what the dominant soil type is. And so you remember when we talked about the web soil survey for the Russell, that's actually, you can get the information from that if you wanted to. That soil map that I showed you before, you can actually, under the soil qualities and properties, you can figure out what soil type you have and what the hydrologic soil group is. So basically, what NRCS has done is they've mapped all the soils in the U.S. as being in one of 4 different hydrologic soil groups. So that's what we mean here by Group A, Group B, C, D. Group A soils are basically your sandy soils, high permeability, high infiltration, and so those are basically Group A. And the other end of the extreme is Group D, which would be more of your clayey soils. So low infiltration, high runoff generation. So that's, a lot of the soils in the Central Valley of California would fit into this group here. And then B and C are sort of in between there. And so the web soil survey is a good source of information for that. That's another, just like we found the K factor for the soil, there's actually another section of the web soil survey that'll give you the hydrologic soil group that's associated with each map unit, so that's kind of handy. The other place to look for that information would be going into the drainage study. If you have a drainage study that's been produced for a particular project, you will probably have the hydrologic soil group in there. This method, it's worth mentioning that the runoff prediction method within the calculator is called the runoff curve number method, and this is something that was generated back in about the 1980s by the U.S. Department of Agriculture to predict runoff volumes. There's also a way of using that method to predict peak flow, but this whole design standard and methodology is dealing with runoff volume. So basically how much cubic feet is coming off the project, both pre and post project conditions. So hydrologic soil group is what it's asking for here. So you pick the dominant soil type. So it's asking you to make a judgment as to what is your dominant soil type. So you might have a mixture of B and C, but it's asking you what is the dominant soil. So if you have, say, 75% C soil and 25% B soil, you'd be picking the C soil input. So for in this case, let's say it's C soil. And then it's asking you what the dominant non-built land use type is. So in other words, on that area that doesn't have impervious surface, what's the dominant land use type? And so these are all pull-down menus. These are coming right from that NRCS runoff curve number methodology. All these things are in the background working, and what we're trying to do ultimately is create a runoff curve number. And when we get to that box, I'll explain what that all means. But it asks you to select what is the dominant non-built land use type. So in this case, let's say it's got 75% or more ground cover, lightly grazed. So we'll select that one here. Existing rooftop impervious area. So let's say, yeah, there's 0. So it's an area that's being grazed or historically grazed. Existing non-rooftop impervious area. So the calculator is asking you to break down existing and rooftop and existing non-rooftop. And the reason why it breaks it down into separate categories is because there's different credit options depending on what type of impervious surface you have. And so that'll make more sense as we get into those individual credits. So in this case, let's say we've got 0. Okay, so then post-construction, this is actually, we're going to go in, we're going to build a project, and the proposed dominant non-built land use type, let's say we're going to have lawn. Let's see if we can pull that lawn, grass, or pasture, covering more than 70%. Okay. And then proposed rooftop impervious area, let's say we're going to put about 4 acres of rooftop as for this school project. And then a fairly large parking area of, let's say, 1.5. So we'll put that in for the non-rooftop impervious area. So that's going to represent the walkways, the parking lots, basically anything that's impervious and not associated with roofing. And then you're going to hit this compute and save button. And so what it's doing is it's generating the runoff that comes off that site pre-project and then post-project. So if you look at going under this output section here, existing runoff curve number. So the runoff curve number it's a combination of 3 things. It's looking at the hydrologic soil group, which is the A, B, C, or D, which is specified up in section 1E up here. It's also looking at the land cover, and it's also looking at what's called the hydrologic condition, which is not specified in this, but that's really looking at how readily runoff comes off the site. The land use and the hydrologic soil group combined give you a runoff curve number. Runoff curve numbers range from about 30 or so on up to almost 100. So impervious surface is given a curve number of 98. So the higher the curve number, the more runoff you get. So it's a pretty straightforward relationship there. So you'd expect the lower curve numbers to be, sandy soils, a lot of vegetation associated with that. That's going to give you a curve number on the order of, say, 30, 35 or so. Whereas clay soil is going to give you a higher curve number. Impervious surface is going to give you something on order of 98. And actually, in the background, this calculator, all the impervious surface that we specify is given a curve number of 98. So the calculator is basically calculating the runoff coming off the pervious area and then the runoff coming off the impervious area. So output B here, design storm, that 0.89 inches, that's not something that you specify. That's something that's being pulled from the background based on what rain gauge you select. So that's the Beaumont 85th percentile 24-hour duration storm that we're using to generate the runoff volume predictions. And then OC here, it's giving you the pre-project runoff volume in cubic feet. So it's fairly, not a whole lot pre-project. That grazed landscape or lightly grazed landscape is generating about 106 or so cubic feet of runoff for that particular storm depth. And then OG, it's giving you the post-project runoff volume. And so it also, the credits, which we'll get into, and that's really an idea with all this, is you're trying to use all the credits that we'll get into to basically get that runoff volume, post-project runoff volume, to equal or be less than the pre-project. So that's really the whole idea. Some of the things that it's giving you too is the proposed runoff curve number. So in this case, our curve number went from 74 on up to 87, 87.2. Usually, it's a rounded curve number, so it's 87. Which makes sense when you think about it. I mean, we've got about about half the project is going to be open space, but then about 5.5 acres out of the 10 is now going to be impervious surface. So it makes sense that that curve number would go up because all this acreage of impervious is being given a curve number of 98. So a simple proration will give you a higher curve number. And OF is giving you the post-project runoff volume as well. So that's what it spits out. These are output. And the calculator, as you see, the inputs are basically the red boxes. So everything else, everything that's not red is what the calculator is giving you as an output. And then the other thing to point out is the calculator gives you sort of a running real-time update on where you stand in terms of the pre-project to post-project runoff volume. So you see right now it says post-project runoff volume is greater than pre-project runoff volume. Perform the volume credit calculations by working through the links below. And so that's going to give you sort of a real-time check on how you're doing. So, and we'll get us to a success point here where we'll actually get that runoff volume below that 106 pre-project cubic feet, and you'll see, sort of a success green light type thing, and we'll get to that. So let's start going through the credits. now. So the first one is porous pavement. So porous pavement is basically, we've spelled out a number of different options here, and each of these give you sort of runoff reduction credit depending on what type of porous pavement we have. So we've got things like brick without grout all the way up to poured porous concrete or pavement with a 12 or more inch subgrade gravel base. Something like this is going to give you a lot more infiltration and runoff reduction than, say, the brick without the grout on less than 12 inches. I'll put this in for just illustrating how this works. So it asks you in square feet, so I put those impervious numbers in acres before, but we just have to convert that to square feet. So it's 43,560 square feet per acre. So I just wanted to show you. I'll put 10,000 just to show you kind of how it calculates the runoff volume. So I just hit compute and update. And so what it does is it gives you the red boxes are the input, and then the output, it's giving you credit for how much square feet you can take away from the impervious surface that you put in here at this earlier stage. So in other words, depending on what type of pavement material you select, it's going to give you either full credit. So this is the most infiltrative combination here, the poured porous asphalt with 12 or more inches of gravel base, or wash stone. You might ask, how did we get these values? We used some of the literature values, mostly from, there's a group at NC State, Bill Hunt's group, that's doing a lot of research on this. So when this calculator was produced back in 2009, we used sort of the best available information at the time to generate those values. So you don't get full credit when you use the brick without grout, but you do get that full credit when you use something that's more than 12 inches of subgrade gravel base. So that's sort of how it works. So let's move into the next credit. So the other one is the next one is tree planting. So we wanted to give credit for folks using trees. I mean, when you think about it, trees can be used as a stormwater reduction device. We obviously put trees in for a number of other reasons, but there's recognition that tree canopy is one of the best runoff reduction measures out there. It basically it intercepts the rainfall and doesn't even allow it to reach the ground. So there's really few better sort of runoff reduction devices out there. So we wanted to give people credit for putting in trees, and so we kind of broke down trees in terms of whether they're evergreen, whether they're deciduous. The idea is that, okay, a tree that keeps its leaves on year round is going to actually reduce more runoff than deciduous tree, which would lose its leaves in the winter. So I'll kind of show you how that works. We'll put in number of evergreen trees to be planted. It's asking you for a number, and so there's actually a square footage per tree that's associated with that. We'll put 20 and 20 just for kicks, and I'll show you how that works. You're getting more credit for putting evergreen trees in than you are for deciduous. So that shows in the calculator there. Again, this is your output file. So it's basically, SMARTS is giving you this running total of the number of, or the amount of credit towards that impervious surface you're putting in. So it happens to be, we've got it taken out to the 4 decimal points, which might be a little bit excessive, but that's okay. It all sort of works out in the end. So it's keeping this running tally here. So yeah, trees are a really good runoff reduction device. We're not the first agency to identify that and give credit for that. It shows up in the city of Portland, has some tree credits in their stormwater ordinance. Back east, the Center for Watershed Protection in Ellicott City, Maryland, generated a whole sort of runoff reduction credit procedure that the state of Maryland and some of the Mid-Atlantic states have adopted. So yeah, we're certainly not the first folks to dream this up, but we wanted to allow that in this iteration of the permit. So the next one is downspout disconnection. So what this is basically, if the project can allow the runoff to flow into sort of a pervious area and infiltrate, that's something that we wanted to give credit to designers for doing. Instead of getting away, or we really want to get away sort of flood-centric runoff management. Instead of just routing all the runoff to a single design point, running it into a culvert, we wanted folks, encourage folks, and be able to take credit for distributing that runoff that comes off impervious area and actually have it drain into pervious areas. And so the credit for this particular credit, or the runoff reduction credit, shows up in the soil quality worksheet. And I'll show you how that works when we get to that. That's the last worksheet we're going to go through. But downspout disconnection, again, the calculator is all about answering these questions. And so a lot of these things, these questions, came from the Center for Watershed Protection in the Maryland, some of the design standards back east. A lot of these are based on that, the questions that have to be answered for those credits. We basically replicated that for this. So the first question is, do the downspouts and any extensions extend at least 6 feet from a basement, 2 feet from a crawl space? So there's obviously some structural considerations when you're using this. We certainly don't want water ponding up around foundations, and we have a whole host of structural issues with structures. And so we want to ask people, okay, are you taking that into consideration? Are you making sure that that water is draining away from a structure? So I'll select yes for that. And then it's asking if the area of the rooftop connecting to each disconnected downspout is 600 square feet or less. The idea with this is, if it's more than, say, 600, the idea is that, well, maybe it's not going to be sort of distributed flow, and it's going to be more channelized, and it could end up just going directly into our storm drain outlet at the end of the project. The idea is that there's a certain amount of square foot of impervious that's going to generate runoff that can be handled in sort of a distributed sheet flow fashion. Okay, so again, that came from a lot of the Maryland work, Center for Watershed Protection work. I'm going to say yes for that. And then it's asking if the roof runoff from the design storm is fully contained in a raised bed or planter box, or does it drain a sheet flow into a landscape area large enough to contain the roof volume for the design storm event? So we'll say yes, and this is basically a check to make sure that you're actually draining it to an area that can manage it. And so I'll show you how that's done. It's basically that volumetric calculation is accomplished in the soil quality worksheet, which we'll get to. So I'll say yes. Let's go yes again. Sorry about that. So it's doing the real-time updates, and then it's asking you for the percentage of rooftop with disconnected downspouts. Okay, so let's say it's 100. Let's say we're overachieving here. We're basically disconnecting all the downspouts on this particular project. And so you don't have to enter an acre amount. The calculator is actually going up and referencing, when I say 100% here, it's basically going to that 4 acres right up there. And so it's taking 100% of that 4 acres. So if we compute an update, it gives you a equivalent volume in cubic feet. So that's actually quite a bit. But again, it says the credit will be provided in the soil quality worksheet. So we're looking pretty good here. Okay, so we'll work down through these other credits. Let's just go, we'll ratchet that back a little bit and say, okay, we've got 25% of rooftop disconnected. So I'll hit that. Okay, so the next credit we're going to talk about is the impervious area disconnection credit. So this is basically dealing with our non-rooftop impervious area, so things like parking lots and some of the walkways that we mentioned before that we identified. And so this credit, again, asks you a bunch of questions that sort of, if you answer yes to them, you can take the credit. So we'll go through these one by one. So the first question is, does the maximum contributing impervious flow path, or is it less than 75 feet? And if it's equal or greater than 75 feet, is there some kind of storage device or some kind of like a trench or a bioretention area available to take that flow that's concentrated and sort of distribute it as more sheet flow? So the assumption here, and this is based on the literature, that any flow that flows longer than 75 feet on an impervious area is going to start sort of coalescing and becoming more of this shallow concentrated flow. And the idea there is that it's, once you get to that point, it's a little bit harder to get water in the ground. It's flowing faster, it's more concentrated. Sheet flow is definitely what we're looking for to actually facilitate the water infiltrating into the pervious area. So for that one, we're going to select yes. Next question is dealing with the area of impervious area. So is the area to any one discharge location less than 5,000 square feet? So that's, again, getting it the assumption that anything over 5,000 square feet draining to a point is going to be more of a concentrated flow situation versus sheet flow. So we'll say yes, we're going to achieve that. And so this has implications for how we grade things, right? So instead of getting away, we're sort of getting away from just concentrating things in one point. We actually want to make sure that we've got less than 5,000 sort of micro drainage area going to a certain point. So that's what that second question is dealing with. The third question is dealing with how is that design storm event runoff draining? Does it drain as sheet flow? It's just another check, making sure that you're draining it to a landscaped area large enough to contain the runoff. And so we're going to select yes. And this is actually a check that's done in the soil quality worksheet. We'll go through that. There's actually a volumetric check on this, and so I'll show you how that's done. These are all sort of tied. Both impervious area disconnection and the downspout disconnection are tied to the soil quality, what you have there for available soil water quality volume. So we'll get to that at the end of the training. The fourth question is, will the stream buffer credit, this is a little bit confusing, so you have to read this very carefully. It's sort of a double negative, but it's saying the stream buffer credit will not be taken in this sub-watershed area. What this is referring to is, it's asking you, are the runoff that you want to deal with through this impervious area credit, are you also going to use a stream buffer to deal with that? And so what that's trying to do is prevent double counting of that. So what we want to do, that's not to say you can't use the stream buffer elsewhere on the project. When we get to that credit F, you see 2 credits from now, we'll simulate that. We'll say, okay, there's a stream that's running on the perimeter of the project that we might be able to drain a portion of that impervious area to a stream buffer and get credit for that. But this is really this particular question is asking the runoff that you want to deal with the impervious area disconnection credit. It wants to make sure that you're not double counting and using the stream buffer credit towards that, because they're kind of the same. They're very similar credits. So I'm going to answer yes for that. There we go. And okay, percentage of the proposed non-rooftop surface area disconnected. So let's say we're going to get about 50% of that. We hit compute and update. And so there it gives us a number in equivalent volume. So it's sort of holding that still. And so remember, this gets basically the credit if we are able to take it in the end. And we'll show you that the final check is done down in the soil quality worksheet, which we'll get to. But it'll be provided in the soil quality worksheet, so we'll get to that. So anyway, this is what, so specifying this, there's a potential of knocking the runoff volume down 1,800 cubic feet, which would actually, you look at our totals, we need to get it down to 106. So if we can take that credit, we're actually going to meet that standard. So we'll get to that point. The next credit I want to talk about is the green roof. And so here the questions deal with, the first one deals with whether the slope is less than 15% or does it have a grid to hold the substrate in place. The idea is that there's some basic design considerations that go into installing green roofs. Probably one of the most important ones is to make sure that that roof slope is flat enough so the runoff is actually going to stay within that roof. Or if it's steeper than that, does it have a grid to hold that substrate in place, that plant medium in place until it forms a thick vegetation mat. So for this we'll say yes. I don't think I'm going to take this credit for this particular project, but I just want to show you guys what happens when we do. We'll zero this out in the end, but we'll go through simulating that we will use this. It says, second question is, has a professional engineer assessed the necessary load reserves and designed a roof structure to meet the state and local codes? So we'll say, of course, yes. This is all above board. Third one is irrigation needed for plant establishment? And usually we need that. I mean, a lot of our plants that we use for green roofs consist of sedums and things that are sort of water tolerant or climate adapted, but we usually need some kind of irrigation to get it going, so I'll put yes. And it's asking for the percentage of the proposed rooftop impervious area that is green roof. So you put in a percentage, and it's pulling from, it's basically whatever percentage you put in. Let's say it's 10% of the rooftop area. It's taking 10% of the 4 acres that we put in the project description or the project box up here in the previous step here, the input screen. So 10%, if we do compute an update, it gives you a credit volume. So in this case, it's almost 696 cubic feet. So I think this might work out on some projects. Just for illustration purposes, I don't think we're going to take this, so I'll basically go out and zero that out. But that's something you might want to play with at your leisure. So we'll compute and update that and just zero that out. But the green roof is also something that the water board allows you to take credit for. Okay, stream buffer is the next one. And so the stream buffer, so the water board's working pretty actively on coming up with methodologies to kind of defensively size stream buffers and for different types of beneficial uses, whether it be for water quality or flood control or wildlife habitat. At the time this permit was issued back in 2009, we sort of did sort of best professional judgment on how we could size a buffer to deal with runoff reduction. So in this case, it's tied to the flood-prone width, and so the calculator has a couple definitions embedded in this particular credit. So the first is flood-prone width. So flood-prone width is the width at twice the bank-full depth. So if you look at a stream channel and you can identify the bank-full depth in the field, and so the bank-full depth is the depth of flow that's associated at the bank-full width of the channel. So bank-full is kind of a geomorphic term, and it really gets at the depth of flow that's responsible for channel form and function, and that's pretty variable. I mean, we have a whole sort of universe of different stream types in California, and sometimes it's difficult to identify this in the field. But if you can identify bank-full depth in the field, the flood-prone width is basically the width at twice that bank-full depth. So let's say we have a bank-full depth of 2 feet of the channel. Flood-prone width would be the width that you would get on the floodplain at 4 feet. Okay, so we basically, if you can imagine, you're in the channel, you're going to go up 4 feet, and then you're sort of going to extend laterally to see where that line is on the floodplain. So it's going to be, there's an associated width associated with that, and so that's what we use to define what that stream buffer is. And so that's one way to do it. We're not, there's certainly other ways to size buffers, but this is the one we picked for the calculator. So it's either the flood-prone width or it's 500 feet, whichever's larger. So in some cases you could have something that's 500 feet wide, or it's tied to the flood-prone width. So that's sort of the first order delineation of how wide we need to go to constitute a buffer. And it's also saying that you've got to drain that water into that buffer as sheet flow. Okay, so we'll say yes for that. Is the contributing overland slope 5% or less, or is it greater than 5%? Is a level spreader used? So this is getting at some of the other things we talked about with impervious area disconnection. Is that water flowing as sheet flow? If it's concentrated, it's going to less readily infiltrate into the ground, so we'll select yes for that. Is the buffer area protected from vehicle and traffic barriers to reduce compaction? So one of the things, the number one things you can do to really reduce runoff reduction is compact the soil. So what we don't want in a soil buffer area is to have something compacted to 95%. This is something where an area where you want to have really good soil porosity and maintain that. And so protecting that is critical for having this buffer function in terms of runoff reduction. So we'll select yes for that. And then there's a question about, is it going to be maintained in an ungraded, uncompacted condition in perpetuity? So this is where we're going to select yes, and we you basically want to have some kind of proof that you're going to be able to do that. So that's something that would probably be in the some kind of covenant or some kind of easement, and just demonstrate that that is going to be maintained in an ungraded, uncompacted condition in perpetuity. And so that's important to select yes if we're going to take the credit for that. You basically have to select yes to all the questions to be able to take this credit. And so for percentage of the proposed impervious area it's going to drain the stream buffer, let's say it's just a corner of the project. So let's just say it's about 5%. So we're saying that 5% of that 1.5 acres of impervious area is draining to a stream buffer. So what that's going to do is, if we hit compute and update, we are going to get a total volume associated with that, a credit volume. So in this case it's 683 cubic feet. So yeah, stream buffers are a really, I think, important component and something that can be incorporated into the site design. It's going to achieve, it's kind of like trees. It's going to achieve a number of different interests if you can successfully install and maintain them and have them as part of the site design. Certainly wildlife habitat, water quality, runoff reduction. There's just a number of multiple benefits that stream buffers can achieve. The next one is a vegetative swale. And so with this one, we are basically deferring to, the first question deals with how you're going to design this particular swale. And so there's a lot of different swale designs out there, but the calculator defers to what's in the California Stormwater BMP handbook. And so we defer to the TC30, which is basically the number and for the vegetated swale. And so that's really the first cut. You basically have to state that you're going to design it according to that specific design criteria. So we'll click yes for that, and then it's basically saying you can't have velocities that exceed 1 foot per second. So that's a design element that's got to be achieved. So we'll click yes for that. Like the green roof, I don't think we're going to take this, but this is certainly an option that many of you have probably used in other projects. Certainly when you have some space constraints, or maybe you're linear in nature and you basically are doing something alongside of a road, a vegetative swale makes an awful lot of sense. So in this case, I don't think we're going to take it, but I will, just for kicks, put in the proposed impervious area that's going to drain a vegetative swale. Let's just say it's going to be 10%. We hit compute and update. And so what that's doing is it's looking at the impervious surface area that is draining to that swale and giving you credit for that. So it's 1,300 plus cubic feet. So that's another option that folks can use to achieve runoff reduction. So we're not going to do that here, but that kind of shows you it's kind of a presumptive thing. It's basically saying that if you design it according to California Stormwater BMP design criteria, we're good with that. So that's how that one works. Pretty straightforward. And that logic, I'll just add that's actually something that Maryland Center for Watershed Protection, when they came up with their runoff credits, they have a similar credit to that. It's sort of if you design the swale according to certain design procedures, you can take full credit for that. Rain barrels and cisterns. This is a pretty straightforward one. I don't think we're going to take this one, but I'll show you how the credit works. It asks you the total number of rain barrels or cisterns. Let's say we're going to use 10. Average capacity of rain barrels and cisterns in gallons. Let's say we're using small little rain barrels that are at near the downspouts, or it's going to basically just do localized storage of rainfall. So let's say they're 80 gallons or so. So what that does is that's going to take the runoff volume in gallons and then convert that to a credit volume in cubic feet. So 96 whoa, that's a lot of decimal points, but pretty exact answer here. But it's giving you the cubic feet that you could take credit for. But I think we'll zero that one out. But that's another option, especially for small kind of residential projects. And certainly with the drought upon us and future drought cycles, I think sort of rainwater harvesting is going to become a lot more important and a lot more prominent in site designs these days. So that's something that the Water Board wanted to allow us to take credit for, allow designers to take credit for. Okay, so the last one we're going to talk about is soil quality, and as we've been alluding to, this is tied to some of the other impervious area disconnections that we talked about further. So let me explain how this one works. I'll give you a little bit of background. I mean, the Water Board is interested in giving folks an incentive and credit for maintaining and improving soil quality in terms of creating nice porous soils, drought-resistant soils that are going to be better for plant growth. They're going to retain water a lot better. So some of the elements in here really are getting at that interest. So here's a red. Let me just read this little note at the top because this is kind of important to go over, because the soil quality credit is really dependent on this interplay between these other elements here. So it says if the soil quality volume is larger than or equal to the sum of the downspout disconnection, impervious disconnection, and landscape area rainfall volumes, then the credit will be provided for the sum of all those three. And if that's not true, then the credit will be provided for just the soil quality volume. So let me quickly go over the landscape area rainfall volume, because we haven't talked about that. So what that is if we have a certain amount of landscape area on the project. So in this case, we can fairly easily figure that out by looking at, it's a 10-acre project. We have 5.5 acres of impervious. So that means that 4.5 acres are pervious. And so the landscaped area, in other words, it's landscaped, it's not paved over. The landscape area rainfall volume, what that is it's that design storm depth at 0.89 inches that we got from the Beaumont gauge. That's the 85th percentile 24-hour duration rainfall event. It's that rainfall depth applied to that 4.5 acres of landscape area. So what it's doing is it's looking at the amount of rainfall volume that's going to infiltrate sort of on the spot there, incidental rainfall volume that's infiltrated. So that's what landscape area rainfall volume means. And so what this is doing, this little red note here, is saying, well, let's first do a check on how much volume is available in that landscaped area to accommodate the volume from downspout disconnection, impervious disconnection, and then that sort of incidental precip volume that's fallen on the landscaped area. So that's kind of how it all fits together. And so then there's a whole series of questions that get at how much volume is available in that soil, and we'll go through each of those one by one. So first is, will the soils be used that are used for landscaping meet the bulk densities listed in Table 1 below? Table 1 comes from some soil guidance put out by NRCS. I think this is a table from some of their urban soils guidance, but it has bulk densities for different texture soils. And so bulk density is related to porosity. So I'll give you an example. For silt and silt loam, we have a bulk density of 1.3. That's going to give us a porosity in the soil of about 50%, because it's basically a relationship between the bulk density of the soil and the bulk density of the mineral parts of the soil. So suffice to say, there's this relationship between bulk density and porosity. Porosity is a lot harder to determine in the field. Bulk density is really not that hard, so we use a quickie equation that relates bulk density to porosity. So 1.3 bulk density is going to give you a porosity of about 50% or so. So, what happens when we compact the soil, we change that bulk density quite a bit, and we impact the porosity there. So ideal bulk densities are basically bulk densities for different textures of soil that hasn't been compacted or altered. And so that's what we're really looking for. We're having folks look at the type of soil they have and what the bulk density is. So that question we will answer. Let's answer yes for that. And then it's going to say, okay, do you know the area weight bulk density within the top 12 inches for soil used for landscaping? We'll say yes for that. And then what it's doing, it's going to give you another question to answer. Area weighted bulk density. We'll say, yeah, let's just say we're dealing with silts and silt loams, so we're 1.3. Looks like 1.2 is there before. I'm going to go in there and basically change that. The other, again, the red boxes are the input boxes. It's asking a couple more questions. It's asking the average depth of the landscape soil media. So let's say recall that this is a project that was previously, or a landscape that was previously grazed, so it's probably a little bit compacted based on animal traffic. And so let's say the landscaped area, we can go in there and amend the soils with organic matter and start improving the porosity of that soil. And let's say we can do that down to a depth of about 12 inches, which is, realistic. You could till things in and one-shot tilling. You don't do repeat tilling because you'll kill the whole idea of soil quality too is sort of the soil microbial thing, which folks have maybe heard me talk about before, but the calculator doesn't really get into that, but it does ask you for a depth of how deep in that soil are you going to have this bulk density. So we'll put 12 inches or a foot, which is kind of realistic. You can achieve that. And then it's asking for the total area, the landscaped areas meeting the criteria. So let's say we've got 4.5 acres of landscaped area that meet that criteria. So let's say we can basically get all that landscaped area. We'll put 4. Okay, so not the entire amount, but we'll put 4 acres. So we'll hit compute and update. And so what it's doing is it's calculating that soil equivalent volume. And so that's basically the volume in the soil that's available. And then it's looking at the downspout, disconnection, and impervious area. And it's giving you a total credit volume because it doesn't have a separate box for this, but it's also incorporating what that landscape area rainfall volume is. So this is what you want. You want this green, nice green, happy message that says that your post-project runoff volume minus the volume credits is going to be less than or equal to the pre-project runoff volume. So in this case, we met it by a long stretch. And so I think one of the things, hopefully by going through this, it demonstrated to you that it's really pretty straightforward, and it's sort of you can go through, claim different credits for what you're going to do, but there's really an emphasis on soil quality and improving soil quality, and some of these credits do really depend on the quality of the soil draining into there. So with that, I'm going to thank everyone for their interest and patience in working through this, and thanks again.
To learn more about California's water issues and the state and regional water quality control boards, go to youtube.com and check out other videos created by Board Web Support.